Hey guys, welcome back to another lecture video for Chem 115. In this lecture video, we are going to learn how to relate the standard cell potential to that of an equilibrium constant. And so this relationship is made possible through our thermodynamic parameter, delta G, or the change in Gibbs free energy. And so if you guys recall in the thermodynamic chapter, there was an equation such that the change in Gibbs free energy is equal to negative RT, natural log of K. And this K can represent any equilibrium constant that we've discussed in this entire semester. And so in the previous lecture video, we observed that the max work for an electrical system can be represented by the change in Gibbs free energy. And so since the change in Gibbs free energy is equal to negative NF E cell, since both of these are the same delta G's, we can go ahead and relate both of these equations to each other, such that the negative value, so negative NF E cell, is equal to negative RT natural log of K. And so if you wanted to solve for example, E cell, it would be, we're going to take this negative NF and divide it to the other side, resulting in RT over NF times that by natural log of K. And so when you guys divide the negative NF over, the negatives will cancel. Okay? And so overall, this term here should be positive. Now, the only way that your E cell can be negative is it's dependent on the value of the natural log of K. And so if you take a natural log of a specific value and it gives you a negative value, then you're going to get a negative E cell. But overall, this term is going to be positive. All right, so we're going to go ahead and just identify the parts here. So R is another gas constant. It's actually the same, it's not another gas constant, it's the same gas constant that we've been using to express things in energy units. So the value is going to be 8.314. And so this is going to be joules per mole times Kelvin. This temperature is going to be in Kelvin units. N is moles of electron transferred. And F is going to be Faraday's constant. And Faraday's constant is 96,485. It's going to be coulombs per mole of electron transferred. And we know that Kc is unitless, or any K value, any equilibrium constant value is unitless. And for the standard cell potential, that's going to be expressed in volts or joules per coulomb. Okay. And so we can also solve for Kc. And so this equation is going to be used if you're trying to determine the standard cell potential. And so if you wanted to solve for Kc, for instance, we can go ahead and go back to this relationship. Excuse me. We can go back into this relationship and move negative RT over to the other side. And then we're going to E both sides to get Kc. And so Kc is equal to N F E over RT. So the negatives will cancel when we divide them. And then we're just going to E both sides. Okay. And so I kind of wrote this equation just a little bit weird, so I'll just move it around. All right. And so if you guys want to solve for Kc, you're just going to multiply N, F, and E cell, and then divide that by RT. Once you have everything inside that fraction solved and reduced to one number, then you guys are going to take the anti-natural log, and that should give you the value for your Kc. So we're going to go ahead and learn how to apply either of these equations to a specific chemical reaction. So first we're going to calculate Kc. So since we're calculating Kc, we're probably going to be using this equation. So we're going to calculate Kc for the redox reaction that's given below. And so for me to calculate Kc, I need the value for N. I need to know the value for F, E cell, R, and T. Okay. And so that's dictated from all of this here. So I need N, F, E cell, R, and T. So let's go ahead and focus on what we can solve for. So we know that F is Faraday's constant, which is 96,485. Why do I keep on writing joules? 485 coulombs per mole of electron transferred. R is going to be 8.314 joules mole Kelvin. T, since we're under standard conditions, that's going to be 298.15 Kelvin. So really the only thing that we don't know is the standard cell potential and the number of electrons that's transferred between the two half reactions. And so before we can solve for Kc, we need to figure out what N is, and we need to figure out what E cell is. And so let's go ahead and try to solve for E cell first. So we know that the standard cell potential can be calculated by the difference between the reduction potential and the oxidation potential. For us to use this, we need to know what's oxidized and we need to know what's reduced. So let's figure that out first. So looking at my oxidation numbers, I know that my oxidation number for copper in solid form is 0. Silver, +1 charge, that's +1. Copper, 2+, +2. Silver, solid form, that's 0. And so if I compared copper before and after the chemical reaction, notice that my oxidation number went from 0 to +2. So since my oxidation number is going up, then this is describing oxidation. And so here for silver, if I'm looking at my oxidation number, notice that it's going down. It's going from 1 to 0. So this is going to be reduction. Let me erase this real quick. So now that I've determined what's oxidized and reduced, I can probably use my reference sheet for my standard reduction potentials to fill in what I need to fill in into this equation. And so I'm going to go ahead and look at reduction first. So notice that for reduction, I'm looking for silver plus 1 with a transfer of 1 electron. And so this is my reference sheet, my standard reduction potential, and I'm looking for silver. And so it looks like silver is right here. So the reduction potential is going to be 0.80 volts. Now I need to figure out the potential for oxidation. And very similar to what I've discussed in prior lecture videos, since copper 2 plus, I'm sorry, let me take a step back. Since oxidation is occurring in the forward direction, for me to use this correctly in the standard reduction potential reference sheet, I need to look at it going backwards. So I'm looking for copper 2 plus being converted into copper with no charge. So the reason why I'm looking at it backwards is because this is referring to the reduction potential, not oxidation potential. And so if you guys scroll through this list, there's actually 3 different types of copper. There's a copper there, there's a copper here, and there's a copper here. And so we actually have 3 different values. So which copper should we use? And so if you recall, we're looking for copper 2 plus being converted to just normal or solid copper with no charge. And so looking at this first one that I highlighted, this is not 2 plus, this is only plus 1. And so this is the wrong reduction potential. So we're down to 2. So if you look at this second equation, here we have the copper 2 plus, which is good. But if you look at the product, notice copper plus 1. And that's not what we want. We want copper with no charge in the product side. So that's wrong. So looking at my last equation, my last half reaction, here I see the copper 2 plus, and here I see copper with no charge, so that checks off. So the oxidation potential is going to be negative 0.34. But how I'm going to write it into this reaction is going to be just the positive first, so positive 0.34 volts. This minus sign, that's innately part of the equation, is going to convert the reduction potential into the oxidation potential. So I don't even have to think twice about it. So if I were to put this in my calculator, so here I have 0.80 minus 0.34. So if I were to borrow from the 8, this is going to give me 6, and then this is going to give me 4. So my answer is going to be 0.46 volts. So it looks like I have 0.46 volts for my standard cell potential. So the last thing that I'm going to look at or try to figure out is the number of moles that's transferred between this reaction. Or I'm sorry, not so much between this reaction, but between the oxidative half and the reductive half reactions. And so this is made possible, so I can figure out the number for n, the value for n, by writing out my half reactions. And so looking at copper, so copper solid is going to go oxidation. Oxidation means losing electrons, and so therefore my electrons should be written on the product side. And since the result is a +2 charge, that means I'm losing 2 electrons. Since silver is undergoing reduction, that means that my electrons has to go on the reactant side. And since the result of the reduction produces silver solid, I'm going from +1 to 0. So the only way that's possible is if I were to add one more electron. And so the silver must gain 1 electron for it to become solid silver. So looking at my electrons here, notice that they're not the same. And so we would have to think of their common multiple, which in this case is 2, their lowest common multiple. And so if I were to multiply everything here by 2, I would get 2 silver ions plus 2 electrons to produce 2 silver, 2 moles of solid silver. So now that my electrons are balanced, if you will, that tells me that the number of electrons that's transferred from the oxidative half to the reductive half is 2 moles of electrons. So now that I have all of my pieces, I'm going to go ahead and use this. So I'm just going to go ahead and copy this real quick because I'm running out of room. So I need to go to a different page. And I'm going to go ahead and copy this because I'm trying to solve for Kc. Okay. So using what I have, I'm going to go ahead and now solve for Kc. So I know that my Kc is unitless. So there's really no point to worry about units, just as long as your kelvins are, the kelvins match up and all of that stuff. I think that's the only thing. And then the volts is eventually going to be converted to joules per coulomb. So joules will cancel with joules eventually. Coulombs will cancel with coulombs eventually. And everything else just kind of falls into place. And so since my unit for Kc is unitless, I don't really have to pay attention, just as long as all of my other units I've listed just kind of match each other. All right, so the value for Kc, the first thing I'm going to do is I'm going to multiply n. So n is 2, F is 96,485. And then E cell, I just forgot it, 0.46. Over R, which is going to be 8.314. Times that by T, that's going to be 298.15. Okay. So I've basically plugged in N, F, E cell, R, and T. And so I'm going to go ahead and reduce this before I take the anti-natural log of it. So here in this case, I'm going to take 2 and multiply that by 96,485, times that by 0.46. And in the numerator, I get 8.87662 times 10 to the positive 4. And so in terms of sig figs here, I have 2 sig figs, that's my least. This is an exact number. N represents the exact number of moles of electrons, so you can treat that as a discrete object, which excludes it from our sig fig count. And so it looks like 2 sig figs is what I'm going to record in my final answer. And if I multiply the what's in the denominator, so it's 8.314 times that by 298.15, that's going to give me 2.47, 8819, bunch of other numbers, times that by 10 to the positive 3. And so here I have 4 sig figs, 5 sig figs, so I'm probably going to keep 4 sig figs. But when I divide both of these 2 sig figs is my least, and so therefore I'm going to go ahead and record it as such. All right. And so here in this case, I'm going to go ahead and divide both of these numbers. So 8.87662 times 10 to the positive 4. And then divide this by my answer. And that's going to give me 35.8098, and then there's a whole bunch of other numbers. And so I'm just going to keep my markup here. Now I'm going to E this. And so the value for my Kc in this case is going to be 3. Let's see here, 3.7 times 10 to the positive 15. Okay. And so this equilibrium constant tells me that the equilibrium will lie in the favor of the products. So since Kc is far, far greater than 1, that means that equilibrium, products is favored. And so since products is favored, then my standard cell potential should be positive, right? Remember, if my standard cell potential is spontaneous in the forward direction, then it would make sense that under the perspective of equilibrium, at equilibrium, there should be more products than there are reactants. Here in this case, it's far, 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 far greater than 1. So really it should lie to the right. And so if you look at the value for E cell, notice that it is positive, telling me that the reaction is spontaneous in the forward direction. And so once again, we have this like parallel concept between the standard cell potential and that of the equilibrium constant. And so if your Kc is to the negative 15 power instead of positive 15, then that's telling you that under the perspective of the equilibrium constant, that the chemical reaction is favoring the reactants at equilibrium. But that will not fall in line with what the standard cell potential tells us. And so the sign of your standard cell potential must be parallel to what the value of the equilibrium constant tells us. So if it's spontaneous in the forward direction, then we should see a equilibrium constant that's far, far greater than 1. And so if the sign of E cell is negative, then we should see an equilibrium constant that has that's going to be far, far less than 1. Okay, so let's go ahead and take a look at another example. And so here we still want to calculate Kc. And so to calculate Kc, I'm going to go ahead and use this equation. So I know that I need N, F, E cell, R, and T. And so it looks like this problem, it's already giving me the standard cell potential, which is 0.90 volts. And so I'm just going to go ahead and just write this down. So this is positive 0.90 volts. And so since this is positive, this is telling us that the forward reaction is spontaneous. Okay? And so if we're trying to solve for Kc, now that we know that it's spontaneous in the forward direction, Kc is probably far, far greater than 1. All right. And so Faraday's constant is going to be 96,485. We know that Kc is going to be unitless. So that's why at this moment in time, I'm just excluding writing the units. We don't know what N is. We don't know how many moles of electrons that needs to be transferred. So that's something that we need to figure out. R is going to be 8.314 joules per mole Kelvin. And then T is going to be temperature. Let me just separate that arrow over here. And so the problem didn't really give us what the temperature is, but if you pay attention to that circle above the E, we know that we're under standard conditions. So under standard conditions, we know that temperature is 298.15 Kelvin. And so the only thing that we need to figure out is N, which is the number of moles of electrons transferred. And so for us to do that, we have to look at, we have to look at our oxidation numbers. By looking at our oxidation numbers, we can figure out what's oxidized, what's reduced. And once we figured out what's oxidized and reduced, we can try to balance the half reactions so that we know exactly how many electrons are being transferred. So let's go ahead and start. And so according to my oxidation number, I know that this is -1. And so we came across this situation a little bit earlier in a previous lecture video, but I'll go ahead and go over it again. So actually, let me do this in a different color. So bromine in bromate, since this bromine is the central atom, we actually don't know its oxidation number. It's not -1. This bromine would be -1 if it was in the position of the anion, and it's not like a polyatomic ion. So for polyatomic ions like chlorate, bromate, carbonate, phosphate, etc., your first element in that polyatomic ion, you need to figure out its oxidation number. And so I'm going to put X. I know that the oxygen's oxidation number is always -2. And it's not hydrogen peroxide. It's not a peroxide, so it's not -1, so it's -2. So iodine, solid form, 0. Bromide, notice how it's by itself, it's aqueous. We're going to take its charge as the oxidation number, which is -1. And so I need to figure out what the charge is of bromate. I'm sorry, not the charge of bromate. I need to figure out the oxidation number of bromine in bromate. And so to do that, I'm going to set up an algebraic expression. So for every one bromine, or 1x, so I'm going to add both of these together. So bromine plus oxygen equals to the overall charge, which is -1. So since oxygen, there's 3 of them, I'm going to multiply that by the oxidation number, and all of that equals to -1. So this is -6 equals to -1. X is equal to +5. And so the oxidation number of bromine is +5. And so looking at the oxidation numbers now, we have -1 to 0. So if I just compare the iodines, it looks like my iodine is undergoing oxidation. Now, if I were to look at my bromines, +5, -1, that's a huge reduction. And so now that I've figured out my oxidative and reductive half, I'm just going to go ahead and write that out. So for my oxidative half, I have I minus to produce I2. And then for my reductive half, I have bromate and bromide. All right. Now, unlike the previous examples that we've worked with, it's pretty simple to actually to determine the number of electrons transferred, just because they're all singular elements, right? Unfortunately, in this case, notice that this is diatomic and this is a polyatomic ion. So it's actually a little bit more difficult for us to determine the number of electrons transferred by simply staring at it. And so this is the reason why I asked you guys to review how to balance oxidation reduction reactions in acidic or basic solution. And so if you haven't been able to review that, I mean, I'll show my steps, but please, please, please review how to balance your redox reactions under acidic solutions. And so I posted a link for Tyler D. Witt's video in your lecture videos to watch. That's found in your Canvas shell. So please make sure you guys watch that. And if you guys didn't, that's okay. I mean, I'll show my step, although it'll be pretty quick. So the first thing I want to do is this reduction. So here I have bromate to bromide. Okay, and so the first thing that I want to do is balance all non-oxygens, non-hydrogens. And what that means is basically look at all the elements that's not an oxygen and a hydrogen and balance that first. Well, if you look, bromine is bromine, there's 1 and 1, so that step is done. So the next thing that we're going to do is focus on the oxygen, and we're going to balance the oxygen with water molecules. And so since I have 3 oxygens on the left-hand side, that means I need to add 3 water molecules, on the opposite side. So 3 times 1 is 3. Okay. And so remember, this is all happening inside a solution. So water, the solvent is naturally present. So it's not like we magically created water. It's in there. Now we're just representing it to balance the redox reaction. So the moment you add water, you guys added one element to this reaction that also needs to be balanced, and that's hydrogen. And so we're going to balance hydrogen with acid. And since hydrogen is found on the right side, we need to put hydrogen on the left-hand side. And so we need 6 H pluses. And so please, please, please do not forget about these positive charges. It's very necessary for the last step in balancing these half reactions. All right, so notice that 3 times 2 is 6, so this is the reason why I put 6 hydrogen ions. And so now that I have all of my elements balanced, I need to balance my charges. And so to balance my charges, I'm just going to ignore all of the letters and focus on the signs. So I have 6 positive charges. And then I have 1 negative charge. Remember what's not seen, the coefficient that's not written down, it's implied that there's at least one of them, or one of it. Okay. So I have a positive 6 charge, and I have a negative 1 charge. When you add them together, this is going to be a positive 5 charge. Now looking on the other side, we have 1 negative charge, and we have 3 of water molecules which has no charge. So overall, we just have a negative 1 charge. And so what you want to do is you want to determine the difference between the two. So remember, we're trying to balance the charges. So we have a positive 5 and a negative 1. And the only way that you guys can balance these charges is by adding electrons. And electrons are negative in charge. And so you are going to place the correct number of electrons on the side that has the largest value. And you want to add enough electrons so that it becomes the value that's lower between the two. And so what do I mean by that? So this is a number line. We have 5, 4, 3, 2, 1, 0, negative 1. For me to go from 5 to negative 1, I need 1, 2, 3, 4, 5, 6 electrons. So I'm going to add 6 electrons on the left-hand side so that the sum of this is equal to negative 1. So we're just trying to balance both of those charges. This is the reason why it's super important that you guys write every single charge that is present in your equation. And that's typically where a lot of students kind of fall victim to. And so overall, now that I know I have to add 6 electrons, this is going to be 6 electrons plus 6 hydrogen ions plus 1 bromate ion. So that's everything in the reactant side. And it's going to produce 1 bromide plus 3 water molecules. So this is the half reaction for just reduction. And so we need to figure out how many electrons is being transferred in the oxidative half. So that means we now need to focus on balancing this using the same steps. And so since I have I minus becoming I2, My first step is to balance all non-oxygens, non-hydrogens. So in this case, I have iodines to balance. They're not oxygens or hydrogens. And so on the left-hand side, I have one iodine. On the right-hand side, I have two. So I probably need to balance this by putting 2 in front of I minus. So now that I have that balanced, my next step is to balance all oxygens with water. And as you can see, there's no oxygens. So if there's no oxygens, do not add any oxygens. And since there are no oxygens added, do not add any more hydrogens in the form of hydrogen ions. Okay? You guys are only adding in these water molecules if an oxygen is present, but it's not present on the other side. And so our last step is going to be to balance the charges. And so here, this is -2, right? So 2 times negative. 2 times a negative charge is -2. And this has a charge of 0. So this is 0. And so remember that this is oxidation. So we're going to be losing electrons, right? Anyways, so which of these two numbers is larger? 0 is larger than -2. And so therefore, for oxidation, we're going to put the electrons on the product side. Because remember, oxidation is losing electrons. Losing electrons, you put the electrons on the product side. And so in this case, to go from 0 to -2, I need to add 2 electrons. And so my final balanced half reaction for the oxidative half is going to be 2I minus I2 plus 2 electrons. And so now all I'm going to do is compare the oxidative half and the reductive half to determine how many electrons are really transferred. And so if you look, we have 6 electrons for reduction, 2 electrons for oxidation. So since 6 is a common multiple of 6 and 2, that means that I probably need to multiply everything here by 3 so that this can be transformed into 6. And so we're actually not we're not really balancing the redox reaction in full like you guys did in the first semester of general chemistry. We are simply performing these critical steps so that we know how many electrons are going to be transferred between the two half reactions. And that's going to give us the number of moles of electrons that we need to put in our equation. And so at this point on, I don't need to go any further. I know that I'm transferring 6 electrons. And so let's see here. I did all of that work just to get one number, which is 6 moles of electrons. It's real work. Anyways, so now that I figured out all of my values, I'm just going to plug everything in. I'm going to multiply everything that's in my numerator. So it's going to be 6 times 96,485 times this by 0.90. So in my numerator, I have 5.21. 0.019 times 10 to the positive 5. So it looks like 2 sig figs is in order. And so for the denominator, you guys are just going to multiply these two. And so this is the same as the previous example. So let me just plug that in there. So that's going to be this number right here. So I'm going to copy this. Okay. And so now that I have both of these pieces, I'm going to go ahead and divide them and then take the anti-natural log. Okay. So I get an E of 210.188, a whole bunch of other numbers. And so when you guys take the E of this number, you guys will get a crazy large number. It is going to be 1.9 times 10 to the positive 91. So this is really telling us that the reaction is going into completion. And at equilibrium, there will be products that's favored greatly compared to the reactants. And so in terms of the value for Kc, it's far, far greater than 1, letting us know that at equilibrium, products is favored. And so if products is favored, then it would only make sense if the reaction is spontaneous in the forward direction. And that is highlighted in the sign of the standard cell potential. All right. And so there is one more problem that I would like to do. It's going to be this one. This one is just going to be a little bit involved. So feel free to, pause this video. You can do it yourself. And you can just fast forward to the answer if you guys just do it on your own. All right, so I'm going to solve for K. And so since I'm solving for K, I'm going to be using this equation again. Actually, so the only thing that's changed is the value for E cell. And so this lets me know that the value is negative 0.365. And so if the value is negative, we know that the forward reaction is non-spontaneous automatically. And so if the forward reaction is non-spontaneous, then the K, the value for K, is going to be far, far less than 1. So this is going to be our predicted value. It should be times 10 to the negative something. All right. And so we're going to go ahead and just figure out what the value of n is. And so to figure out the value of n, we need to know what's oxidized, what's reduced. And so there is actually a shortcut especially if you guys are working with two reactants and two products for oxidation reduction. And so your chromiums, so the main element or the metal, this technique only works if there are two reactants and two products. So I just want to make that clear. And so if you guys don't like listing out the oxidation numbers, then a quick way to determine the oxidative half and the reductive half is just by combining all of the metals that are the same. So since chromate it has chromium and chromium solid has chromium, then these two that I've highlighted in pink are probably going to form a half reaction. Whether or not it's oxidation or reduction, I actually don't know because I didn't do my oxidation numbers. And so that's the fault in this method. I just don't know what's oxidized and what's reduced. And so just to expedite the process in terms of solving the value for N, I know that I know that dichromate, not chromate, is going to be paired up with chromium solid. So this is one half reaction. And therefore, manganese 4 oxide and manganate, permanganate is going to be another half reaction. The downside to this technique is that I don't know if it's oxidized or reduced. And so first step, balance all non-oxygens, non-hydrogens. So here in this case, my chromiums needs to be balanced, so I need 2 chromiums. So now that my chromiums are balanced, I need to balance my oxygens with water molecules. And so since the right side does not have any water molecules, I need to add 7 H2Os. And so that will ensure that I have 7 oxygens, which balances the 7 oxygens here. And so since I've added hydrogens, I'm going to go ahead and balance that with H pluses. And so I need to make sure I have 14 H pluses to balance the 14 hydrogens that's found on the right side. Now that I've balanced all elements, I'm going to go ahead and balance the charges. So on the the left-hand side, I have 14 positive charges, and I have 1 -2 charge. Right? So I have 1 -2 charge. And so I'm just going to put -2. Here I have a 0 charge and I have a 0 charge, so this guy is going to be 0. And so if I combine these together, this is going to be 12. So I have a positive 12 on the left-hand side and a 0 on the right-hand side. And so to balance my charges, I need to add enough electrons to make sure that the higher number becomes my lower number. And so the only way that's possible is if I add 12 negative charges in the form of electrons. And so it looks like I have to add 12 electrons on the left-hand side. And so if 12 electrons are being added on the left-hand side, then this is actually a reductive half, right? Remember, reduction is gain of electrons. So this is 14 H plus, let's see here, 12 electrons, plus so this is my reductive half reaction. And why is this reduction? Well, because I'm gaining electrons since it's found on the left-hand side. All right, and so I'm going to go ahead and compare these two for the oxidative half. And how do I know it's oxidative half? Well, because I figured out that the dichromate into chromium is reduction. So I only really have one thing left, which is oxidation. And so let's see here, I have MnO2 to produce MnO4. So no charge, charge is -1. You always want to pay attention to your charges. First thing is to balance out my non-oxygens, non-hydrogens. They're both balanced, 1 and 1. And so here I have 2 oxygens, here I have 4 oxygens. My oxygens are not balanced. So I need to add 2 water molecules on the left-hand side. And that's going to equal to 4 oxygens. So 2 oxygens plus 2 oxygens is equal to 4 oxygens. Next, I need to add hydrogens. And so I need to add 4 hydrogen ions on the other side. And so now that I have all my elements balanced, I need to balance my charge. To balance my charge, I'm going to look at my overall charge for each compound. And it looks like on the left-hand side, I have 0. On the right-hand side, it looks like I have, let's see here, 4 positive charges. And here I have 1 negative charge. So overall, this is going to be +3. And so I'm going to compare my values, my charges, my overall charges, and I'm going to make sure that the larger number becomes the smaller number. And the only way that's possible is if I add 3 electrons or 3 negative charges. So -3 plus 3 is equal to 0. And so overall, I'm going to get 2 water molecules plus 1 mole of MnO2 to produce 1 MnO4 plus 4H plus 3 electrons. Notice that my electrons are on the right-hand side, so this truly is describing oxidation because I'm losing electrons. Now, if I copy my balanced reductive half, notice that here I have 12 electrons, here I have 3 electrons. They're not the same, but I know that if I multiply the top equation, my oxidative equation, by 4, this 3 electron is going to become 12 electrons. And so it looks like 12 electrons is how much is transferred between the oxidative and the reductive half. And so once you guys have figured that out, you do not need to go any further in terms of balancing your redox reaction. And so this question mark in pink is going to represent 12 moles of electrons. So now that I have all of my pieces, I'm simply going to multiply everything in the numerator. So it's 12 times 96,485 times this by -0.365. Okay. And then I'm going to divide this by the product of 8.314 and 298.15. And so overall, I get a Kc value. And I'm not done yet because I need to take the anti-natural log of this. So this is going to be -1.70486, whole bunch of numbers, times 10 to the +2. So it's -170.486, and a whole bunch of other numbers. So if I were to take the anti-natural log, my Kc value is going to be 9.1. Sorry, it's 9.10, so 3 sig figs. So here 3 sig figs. 9.10 times this by 10 to the negative 75. That's a really small. That's far less than 1. So this is telling you that at equilibrium, the reactant side is favored. And the reason why the reactant side is favored at equilibrium is because if you look at the sign for our cell potential, it's non-spontaneous. So if it's non-spontaneous, then how will products form without some type of catalyst or without some type of input of energy? And so that this is telling you that if you mix these two reactants together, you will probably not get a lot of products. You'll get some, but it's really small. Most of your chemical compounds will still be in the form of the reactants. All right, and so hopefully by going through these 3 examples, you guys know how to implement or apply balancing redox reactions through acidic solution to determine the number of moles of electrons. Everything else really, it's simple. The calculations are simple. It's just the little stuff that we need to pay attention to. All right, so that's pretty much it for this lecture video. I'll see you guys in the next one.